There we go.
Okay, can I continue?
Yeah,
Okay.
go
The
ahead.
title, the title of the paper is Database Processing Memory, Experimental Study. And the history behind this paper is because during my PhD, I found the 3D stack memory. It is a sort of processing memory device. And right now, we are still together yet. It's a kind of memory, you know. Sometimes it's good, sometimes not too good, but we are still together. And our idea behind that is, behind this paper, was to investigate processing memory in database systems. And here we have the 3D stack memory. And okay, I know that several questions may have popped up in your mind. For example, what's this? Why I need it? How it works? How to use it? A lot of questions. And I faced the same situation in my PhD. So this paper and the presentation were proposed to answer some research questions. Okay, here I have the agenda with the introduction and the motivation of our work. After I will introduce the PIN devices, the processing memory devices in details. Then I will press our contributions and conclusions with challenges and opportunities. Okay, let me turn into the database context. During queue execution, database systems access a lot of data throughout the memory hierarchy, and it needs to transfer the data into the processing unit, the CPU. But the memory hierarchy is comprised of memory cache levels and the main memory, and which level has different latency and capacity. For example, to reach a data only present in the main memory, memory requests pay the latency of all levels to find the data and to transfer it into the CPU. And only if the data are present in the CPU uh, registers, the computation can take place. And this happens with all modern queue execution systems that rely on this traditional CPU processing, which implies that they have to transfer all required data around the memory hierarchy. And this is a big problem. And also, it is the motivation for our work because such data transfer leads to the problem of data movement. And you have defined the data movement as a black hole that consumes a lot of resources on database systems, especially for queue execution. For example, our recent work on Google workload has demonstrated that around 63% of total system energy on average is expended on data movement. And there are some cases where other applications waste more than 80% of energy on transferring data, which also leads applications to have a high latency. But don't you worry, we have a possible solution to that. And the solution is based on processing memory devices or PIN devices. These new devices add logical units inside the memory to support the near data processing. And they also can place the main memory by providing ordinary access to support traditional CPU processing. But on the other hand, they can work as the RAM memory that we have today to support legacy applications. This approach can mitigate the data movement problem around the memory hierarchy, and the industry promise to reduce execution time and the energy consumption with this kind of device. And here we have again the 3D stack memory. And now we know why we need it. It is useful to address the data movement problem. And let me now explain how it works and how to use it. Firstly, I introduce some terms of the 2D stack memory architecture. It is composed of 4 or 8 VRAMs chips of the RAMs, and these chips are stacked together forming a memory structure like a cube. And now the chips of the RAM are also connected through the silicon via a new kind of bus technology. This bus can integrate the memory and the logic layer at the same chip inside the memory. And besides the traditional memory organization, rows and columns that we have today, we have another dimension or a new vertical memory partition that is called a vault. Inside the 3D stacked memory, there are 32 interdependent vaults to provide high data access parallelism inside the memory, with a high bandwidth of 320 gigabytes per second, a high bandwidth. And at the base of the memory stack, there is a logic layer to execute near-date instructions, such as arithmetic, logical, and bitwise atomic instructions. And here I am going to show an example in how to run the selection operator with processing memory. And this example is based on Hive. That is an extension proposed at the logic layer of the process of the 3D stacked memory. It was proposed to support single operations inside the memory, vectorized operations. Well, suppose we have our SQL query here, and we need to filter a database column. Firstly, this column is sliced into chunks of 8 kilobytes, and each chunk is split again in segments of 256 bytes. And with that, the organization, we have 32 segments, and we can explore the 32 vaults of the memory and run 32 memory accesses in parallel in the memory. Okay, with that, we can run the loads operations, access each vault, and explore the parallelism inside the memory. And the load operations write the segments of the chunks inside SIND registers, internal SIND registers. For example, the have X here. And then we can perform some SIND instructions inside the memory. For example, filtering the column that we want. In the end, we can store again the memory the result of this filter, or return it to the CPU. And note that the Intel AVX 512 supports SIND register of 64 bytes, which are the widest SIND register present in the CPU site. On the other hand, the pin supports register of 256 bytes, a factor of 4 times, and the operations take place inside the memory without needing to transfer the data into the CPU. And this is our example. I will change to the experiment session. If anyone have questions, feel free to ask.
Just a stupid question. Is it called 3D because, I mean, the picture you showed was very much two-dimensional.
Yes.
Why is it called 3D?
Because 2-dimensional, but you have a 3-dimension. It's like a cube, you know?
Okay, so these cells B1 to like 6, they are like arranged somehow.
Yeah, you have here, we are seeing here the 2-dimension with rows and columns, but we have another dimension, and it's a cube.
Uh-huh.
The picture is not too good, but...
And this is somehow new, sorry for my ignorance, but this is somehow new for RAM chips.
Okay, no problem. I think there are others figured by the hardware supply that show that. I can see and send it to you if you want.
Okay, thanks.
Okay. And the experiments here were based on a simulator, the Sinuca, a cycle accurate simulator. And we have used the TPCH benchmark of 1 gigabytes and 100 gigabytes in some we evaluate the operator selection, projection, BOI, and the aggregation operator on the AVX 512 architecture and on the PIN. And the AVX architecture supports single register of 64 bytes if we use the degree of parallelism up to 8 times using the looping or rolling technique. On the pin side, we have a single register of 255, no, 56 bytes with the degree of parallelism up to 32 times. And this number is the limit of the number of vaults available on the 3D stack memory, 32 vaults. Also, we classify the results according with a taxonomy of operators that considers the memory access of the operators and the data use of the operators, low or high data use. And the experiments were proposed to answer some research questions. For example, the first experiments on the selection and the projection operators were proposed to see the potential reduction data movement that the processing memory device can provide. Both operators have coalescent memory access and the low data use. And here I have this graphic. Let me further explain this graphic because I use the same graphic style in the rest of this presentation. Firstly, it is split into 4 data sets, sometimes in 3. And the data set fits into the caches L1, L2, and the LLC cache. And the last one only fits into the hub. In brief, you have 2 kinds of data sets. The ones that fits into the caches, and the other that only fits into the main memory. And in each data set, you run the operators using AVX and the pin execution. The horizontal X determines the degree of parallelism present in each architecture. And the Y-X has the execution time or energy consumption normalized to the worst execution for each data set. For example, in the L1 data set, the first one, you have the worst execution with the pin using the degree of parallelism in 1. And the others executions were normalized to that worst case. Okay. Let me turn into the projection operator that has similar results of the selection. And for these operators, the execution in pin with processing memory is very fast compared to the CPU processing, around 4 times up to 10 times faster with a high energy saving. And the reason behind that is that both operators have coalescing memory access and no data use at all, which means that they have data streaming behavior. And the pin is very good for this kind of applications. Okay. In another experiment, we analyzed the nested loop join algorithm with coalescing memory access and the high data use. And we choose to analyze this algorithm because it resembles the data access pattern of matrix multiplication, linear transformation, and some machine learning algorithms. And our analysis on the nested loop join can add useful insights to that range of applications. And the results show that while data fits into the caches L1 and L2, the CPU process is better because of data use. But when data starts not to fit into the caches, the pin execution is very faster and expends less energy. An important observation here is that the application still has in situation high data use, but the data use distance reached the cache size limitation. Okay, what is the data use distance? It is the number of distinct memory references that have happened between 2 memory access to the same location. Okay, let me give an example with that. For example, we if the application right now access memory address B, and this same address will be accessed in the future. But before this to memory access of the address B, there are some other memory access, some loads operation. And this number of loads operations is the data use distance. If the data use distance is very high, for example, greater than the L2 cache size, the pin execution starts to be very fast, very good. Here we have another experiment about operators with high data use and random memory access, which is the case of the hash join algorithm and the aggregation operator. Okay, for the hash join, and the CPU processing reach the best performance in all data sets, considering the execution time. On the other hand, the pin execution uses less energy, around 65% less energy. And the reason of that is because the handle access to the hash table inhibits the parallelism of the vaults. You can use all the parallelism inside the memory. Okay, let me turn to the aggregation operator. It has a similar performance in terms of execution time, but it uses less energy compared to the pin execution. And because in your experiments, the hash table fits into the caches. I also performed another experiment, increasing the hash table size, and the pin execution improved a little bit, but not enough to surpass the CPU processing. And finally, we have the operators with low data use and random memory access. This is the case of the sort merge join algorithm. Actually, it has a moderate data use. For it, we have fixed the degree of parallelism in H for the AVX and 16 for the processing memory, and you add more data sets to evaluate it. Okay, the results are the following. When the data set fits into the caches, the CPU processing is faster, around 20 up to 40% faster. And more important is that it saves a lot of energy compared to the processing memory, which is a big energy saver, around of 85 less energy. However, when the data sets do not fit into the caches, the CPU processing start to use less energy. But the execution time continues better with the CPU processing. And these graphics here and the others with the aggregation, the hash join operator, the hash join algorithm, shows that the decision to execute the operations in CPU or in pin is not too trivial. We need to analyze other variables, for example, the cache settings, the dataset size, and the target performance metric to decide where to execute the operators. So this led us to think about a hybrid queue execution system to interleave the execution of the operators between the processing memory and the CPU. Well, okay, here you have a summary of our results per database operator. And this table shows the decision for pin or for the CPU processing. And we have three variables to evaluate: the operator, the data set, if it fits into the caches, and the target performance metric, time or energy. Some decisions are straightforward, for example, the selection and the projection operator, because no matter if the data set fits into the caches or we are looking to improve the time or energy, the decision is always better to run these operators inside the memory, processing memory. On the other hand, if you look at the join operator, the decision to execute the joins is not trivial, because it depends on the operator behavior, depends on the data set, and depends on the target performance metric. Okay, and based on this table, you use it as a heuristics to propose a hybrid queue plan scheduler. It uses the operates profile to interleave the execution between processing memory and the CPU. And here we have these two graphics. They have a breakdown of the execution time and the energy consumption for three query plans. The first plans are hardware specific, that the only executes the operators in the CPU or in processing memory. And the third plan is a hybrid query plan that interleaves the execution of the operations between the CPU and the processing memory device. And we showed that the hybrid query plan can reduce execution time around 35 and 45%. And more important, it expends less energy. If, for example, it can save more than 2 times energy compared to the CPU specific query plan, which is a big energy saving. And now I have the conclusions here. And our conclusions were guided to answer the research questions. And firstly, the results of the projection and the selection operators proved that the pin has potential to reduce the data movement problem around the memory hierarchy, because it can boost the execution time in one order of magnitude of this, with these operators, and also it can reduce energy consumption. Another point is that we identify some relevant characteristics that determines the decision between processing memory or the decision to processing CPU, the operators. And the characteristics are the cache settings, the data set size, the performance metric, and the operator behavior in terms of memory access and the data use. And the last research question is related in how database system can coordinate query execution between the processing hardwares to exploit the benefits of both. And we proposed a hybrid query schedule, which could reduce the execution time and also save a lot of energy. And I think it's our last conclusion, but not less important, because we have identified that the database system requires efficient co-design of database pin to benefit, to take advantage of the pin hardware, and also to mitigate the effects of data movement. And the last is the challenge, the opportunities that we have identified. The first ones are related to simultaneous co-processing, because now we have an environment with heterogeneous processing devices, and in this kind of environment we should avoid idle devices, and we also should detect inefficient power consumptions. In the perspective of query execution optimization, query plan optimization, we have another dimension to analyze, which is the processing unit. And this variable, I think, should be incorporated into the query plan optimizer, which can amplify the search space to find the best query plan. Another point, which is very important, is near data transactions, because the current specification for the pin hardware provides support for near data transactions inside the memory. And now the hardware can handle transactions. And I haven't seen many works in this direction. And a big challenge is how database system can operate with processing memory, or what parts we need to change on database systems to use the processing memory devices. And thanks. Thank you very much for attending my presentation.
Thanks, Tiago.
Thanks, Tiago.
So after these thanks, maybe I should open the floor for any questions.
Okay.
Who dares?
I have a question. Yeah, first of all, thanks a lot for the presentation, Tiago. I have a question regarding the experiment with short merge join, if I recall correctly. Yeah, this one. So in the second section of the diagram, as we see it, where the data do not fit in cache, PIM still seems to require more execution time, right?
Yes.
Why is that in this case?
I think it's because of the behavior of the operator. Actually, the random memory access is not too good for the processing memory devices.
Okay.
And also the operator has a little bit of the data use, which means that some data is still in cache, and the central processor can take advantage of the caching mechanism.
Oh, okay, okay, I see. So it's still, I mean, the fact that you need to, for the data to move from the main memory to cache still is faster than
Yes.
using PIM in this case. Okay.
Because the processing memory device is based on the DDR technology, and accessing a cache or a DDR chip cache is very fast.
Okay.
That's the case.
Thank you.
I have a question. Tiago, about the hybrid approach that you use, I was just wondering if you have some sort of partition between the CPU and the hybrid memory cube in this case, like if they are both executing the same operation together at the same time, or you basically first execute on the hybrid memory cube and then after you do it on CPU.
Yeah, I did the second option because not too easy to synchronize the operations when they have in parallel in CPU and in PIN. You use PIN and after you use the CPU in some case.
Oh, I see. So one future approach would be to try to use this co-processing between them both, I guess.
Yes. I put a point here in the challenges that is carrier pipeline execution systems with both devices. I mean, this point is that direction, choose both at the same time.
Okay, thanks.
Okay, thank you.
This is Stefan. I would have a bunch of questions, but let's start one at a time, and please others interrupt me if you have questions as well. Or I just give you the floor. Thanks for the presentation. It's very interesting. To get started, since it's all about a trade-off between compute capacity and data movement efficiency, what exactly is what are the specifications of the compute facilities on or in the memory? So how can I expect that? So what kind of instruction set, what kind of clock speed, what's on the device?
Yes, I don't remember how of them. And I think you have a table in the paper with a lot of parameters that the processing unit inside the memory uses. I think it was based on processor specification, but I really don't remember the name of them.
Okay, I can look in the paper. I think we have the paper. But that means in turn this is a full-fledged CPU capacity. It's not like single operators, but it is arbitrary.
What I remember is a single processor that executes one instruction at a time. they have a little few support for just for integer operations. They doesn't have floating point units there, because floating point units require a lot of space, and also there is a constraint about the energy with that. And the experiment just run single instructions for integers. That is the support for that the pin hardware provides.
But apparently sufficient to implement all the operators you mentioned on integers.
Sorry?
Sufficient capacity to implement all the operators you mentioned.
Yes.
So
Yes.
there's control instructions and loops and everything.
Yeah, the hardware provides some instruction set. We just use the instructions that are already present in the hardware, which means that we didn't change the instructions or we didn't add any new instructions to it. We just use it as it is, using the instruction set that there is the hardware.
Okay.
Sorry, but Stefan, I mean, I understood that the only instructions that are supported are like these comparison instructions.
Yes, comparison instructions and some add and subtraction instructions.
Yeah, but not control flow.
We have a kind of control flow there. We have some branch instructions, but we almost avoid that, trying to use, how can we say, predicted instructions, transforming the control flow instructions in data flow instructions.
With predication, you mean?
Yes, predication. That's it.
You can kind of simulate branches with predicates, with predication.
Yeah, like bool calculation, you know?
Okay. Well,
Bool calculation.
okay. I was just wondering how you implemented the hash join and sort merge join, so sorting in this kind of environment.
Actually, we used we based on the paper of Sigmod. I think it was proposed by Kepe Ross in Sigmod 2015, and they used the implementations that the guy put there, and they implement a lot of operators using the AVX intrinsic functions that use this style of implementations. I can see the paper here.
Rethinking SIMD vectorization, that one?
Yeah, that's it. Yes, that's it.
Yeah, but that's SIMD style operations, which do not really have control flow. I mean, they may have a mask that tells you
Yes, yes.
on which lanes the operation is supposed to happen.
Yeah, that's it.
Yeah. So so how do we process strings, a column of strings on this device?
Sorry?
How do we process a column? How do we join two tables where the data type is string, a varchar?
We have to do some conversions for integer, like using dictionary or something like that.
Sorry, so conversions. I don't think conversions alone will help you there.
Yeah, I didn't test it with varchars.
Mm-hmm.
I just use integers like foreign keys and primary keys.
Okay. And I mean, if you look at the, I mean, the thing is, I mean, this is nice in a way, but the memory business, I mean, now I just want a reality check here. The memory business is extremely low margin, and price is, I think, everything for a long time in the DRAM. So any complication or any additional kind of real estate or that goes into the DRAM chip, well, needs to be totally minimal. Otherwise, it would drive up the price. So, can you give an estimate from a hardware point of view of how much more expensive or complicated a stacked memory chip with these capabilities would be compared to a plain DRAM chip that you can also stack, of course, but it would not have these functionalities?
Yes, it's a trick question to answer. Right now, I know that some graphic cards has a 3D stack memory inside it. I think AMD graphic card has it already, and it's already able to ship to, right? But I think the memory in these graphic cards don't have the functional units yet. They just use the vault organization. And I don't know when it will be incorporated. I think in the future it will be, but it's very hard to estimate that.
Right. Is there another question, maybe?
I have a question. Let me also show. So I understand that you have finished this PhD actually last December. It's highly experimental and simulation. So as we all know, a PhD topic is finished and then the future lies ahead. So with all that past experience on this challenge, what would be your next adventure? Where do you think actually the next research question is lying ahead of you, which you would like to embark on?
I think maybe it's about transactions, because I haven't seen many works in this direction.
You know, there is a big book of 900 pages written in Germany, which has a full coverage of all transaction schemes.
Yeah, I know.
So where do you see then the challenge?
The challenge here, I think, is how the hardware can handle transactions, because you can avoid a lot of latches on the software side, and use the locks that the hardware can provide to work with transactions. I think it's
So you're looking into transactional memory.
Yes.
And that's where actually the next $10 million businesses will come from.
Yeah, I think so.
And fame.
Yeah, well, hardware is strange. I mean, what we do know about hardware is that it is not driven by the database or the data management kind of business, or which is a small piece of the current kind of even server-side hardware. I think you, going back at my question, I think that these architectures can only become relevant currently if they, for instance, would do something remarkable in machine learning. So do you think that stacked memory can contribute something to machine learning performance training, for instance? If that would be the case, there, I mean, that would be possibly a driver for new kinds of art.
Yeah, I think so. I have see some works about that, and I think there are some computer architecture researches that work with that, and this is good for us, because I think the applications like the selection, projection, and nested join have a similar behavior compared to some machine learning algorithms, because they have a sequential access, a collapse memory access, and a high data use. that is good for these applications on the database side. And maybe we can take advantage of this hardware. Because I think a great point in my work is that you can identify some operators' behaviors and compare the same behavior with other applications. And we can use the hards that are known for other applications and apply the same idea or the same operators to use that hardware. Just compare the behavior of the applications and the behavior of the operators and see what we can do and what we can use with that.
Okay. Are we out of questions or? It seems so. Really?
I think a big pointer of this work is that we didn't change anything in the hardware. We just adapt the database operators to use the hardware to simulate the operations that the hardware support. And this is a good point for us because you can see that we can run the operators inside the hardware as it is specified for that for.
Mm-hmm.
So one last question for me. In the thesis and in the paper, you focused on, of course, in my perception, the worst join algorithm you can imagine. That's called a nested loop join. Well, actually, all database systems will try to do a better job to at least actually use hashing or anything of that case. So what of the results would hold if you would extend your simulation into the more predominant techniques, like using hash-based joins? Will it change the picture completely? So what do you expect?
Yeah, we have some experiments with hash join and software join to see that. And these experiments show this, that some points is good for PIN, especially if you consider energy saving. But actually for execution time, the CPU processing for this range of application is still better. Here we have the sort merging results, and I think here's the hash join. For execution time, CPU is better, and this is the reason behind that is because of the not access to the hash table.
Okay,
But
sorry, I overlooked
it.
Yeah. Sorry, thanks. I think that your results are a bit, well, to be expected in the way that you say, well, scans like filters and projections. These are the operations that will really fit well the PIM and the processing near the memory. And then the other operations, if you look at execution time, they are better done in the CPU.
Yes.
Of course, if you look at memory consumption, then the story is a bit different. And also nested loop join, which is like a scan that you repeat very often. So
Yes.
in that sense, it's not strange that it behaves the same as a filter. So like in these things where you do massive data access sequentially to the memory, then with a filter, then the PIM can help. But yeah, how actually would such a operation work in terms of concurrency? I mean, because it's very low level. You need also to make sure So what happens if on the instruction level in the hardware there? Because you need kind of exclusive access to Vault and to a
Yes.
bank to do this.
Actually, you have to do exclusive access to the registers of the processor. We have to lock the register to do the operations,
Mhm.
and then we can release it for another operation. So concurrency is very complicated there
Mhm.
because of these locks on the CD registers. Actually, we have a test with just a single thread simulation. There is other work that try to put a kind of cache inside the memory chip to avoid this kind of locks
Mhm.
and to support parallelization inside the memory.
So what's the expected overhead of creating these locks?
I think
Because that will cost time as well.
yes, but the lock is just to set a flag on the registers. We'll have a flag that this register is not locked or it is. I think for the hard implementation is very easy. We have any register, our register have a flag if they are locked or not.
Mhm. Right. Okay. So so Mark, would you suppose that this hardware would exist? So would you consider porting, including support for it in Dockerby?
Good question. I think probably not, but it's a big if, right? Depending on how popular it is, how ubiquitous it is. But potentially in the future, if it becomes it comes everywhere, maybe.
Okay. Well, are there more questions? We are kind of getting to the hour as well. Started a bit later. I think there are no more questions. Well, in that case, I would really like to thank you again, Tiago, for this interesting presentation. Very nice result also of the paper on that and getting your PhD. Yeah, and well, you saw the group here, and I think we enjoyed your talk. Thank you very much.
Okay, if you want, you can send me the question by email. No problem for me to answer that.
Yeah. Okay, I will stop the recording now.